Welcome back to the second part of the first session. We continue in English and with presenters presenting digitally. So we are aware that the resolution is not the best for the digital presentations. We hope that we were able to tweak it a bit during the coffee break, but you can also, and especially this goes for you in the back, you can also follow the presentations by the streaming. So the link is not on the website, it's on the email you got when you signed up for this conference. So go into one of your emails and you will find the link for streaming there. So next speaker is Britta Alveog from the University of Tromsø. She has a focus on natural language processing methods. Her current research digs into the viability of artificial intelligence to enable the remote monitoring of patients' cognitive and mental states, specifically by speech. And her talk is on language technologies in psychiatric research. Britta. Vær så god. Vær så god, Britta, kan du høre oss?
Ja.
Ja, da kan du starte presentasjonen din.
Do you see it now?
Yes, we do.
Great, and you can hear me. Can you hear me?
Yes.
Great. So thank you very much for this invitation. So yes, my talk is going to be about language technologies in psychiatric research and the challenges and opportunities of translating this into practical tools. So why are we interested in speech? Well, unlike medical disciplines where advances in technology have replaced the listening to patients, in psychiatry, listening to what patients say, what they say, how they say it, and when they say it remains essential because it's via speech that the symptoms and signs emerge. And since much of the clinical assessment relies to some degree on language, our research over the last 20 years has leveraged natural language processing technologies to provide the proof of concept for methods to better understand the broad spectrum of underlying neurocognitive deficits in patients and to develop tools to monitor patients. Oh, my slides are not moving ahead. Oh, they are now. So 20 years ago, when I was at the National Institute of Mental Health in the US, we started to apply natural language processing methods to the clinical domain in order to improve assessment in psychiatry. And this was the beginning of a very long collaboration with Peter Foltz in Colorado, who was using this technology to automatically rate students' essays. And I persuaded him that together we could actually use this to apply to clinical interviews. So that work basically used natural language technologies to provide a second opinion about illness severity in psychiatric patients. And then after moving to Tromsø, we've translated this proof of concept via a combination of technologies to monitor psychiatric outpatients. So talking a bit about the structure of this talk, this is a roadmap of my talk starting today, starting with a proof of concept for 2 decades ago, which led us to be able to leverage these ideas and to build tools to monitor clinical state. So we have assessed semantic, syntactic, and statistical and acoustic features of language. We have then used this proof of concept to recently develop and trial a mobile app that patients could self-administer assessment tests. This kind of design has enabled frequent and remote administration to monitor cognitive and mental states. And this has enabled us to examine the viability of automating the full assessment pipeline, from test administration to automatic speech transcription, data analysis, and to predict clinical states. And in this process, we've learned that there's lots of useful things we can do, but an enormous amount remains to be done before we can implement this clinically. Notably, we need to have new psychometrics to model dynamical, multimodal and longitudinal data, which we don't have in my field at least. And if our goal is an effective AI-mediated clinical decision support system, then we have to have computational safeguards to minimize the risk of model error. So talking a bit about our work from about 20 years ago, looking at the left here, we started using computational semantic methods to rate the speech generated by patients with schizophrenia. And our goal was to measure clinical thought disorder in an objective and reliable manner. Now, on the left is a visualization of using latent semantic analysis, which was a very hot method at that time, to calculate the word-to-word associations by computing the cosine similarities of these words in a very large text corpora. And what we observed was that patients with a lot of thought disorder generated words that were less associated with each other, and this correlated with their clinically rated thought disorder. Of course, today, with newer semantic models, for those who are familiar with things like word2vec, BERT, and the added bonus of millisecond precision that we can get from automatic speech recognition, illustrated on the right, we can add detailed temporal information into our models about disordered speech. Now, since much of the communication disturbances that are prevalent in psychosis since communication disturbances are prevalent in psychosis and that this is a heritable illness, it's likely that these communication problems are present in those who are related to patients who have these disorders, even if it's just going to be in a muted form. So they're likely to be present in the relatives who are unaffected with this illness, but arguably are at risk. And so we've applied these methods to speech generated from the relatives of psychiatric patients, and we find these very subtle signals that are present in these healthy people, despite them not being floridly ill. So these measures are very sensitive, and that's something that we know, that these methods can pick up something that we as humans can't necessarily detect. We've also applied this approach to compute clinical measures that clinicians compute when they listen to speech generated from patients. This is an example where somebody is telling the story about Cinderella, and we put this in a computational semantic space and compare the transcript against the remaining transcripts for which we have human ratings for. So this is a way of giving the machine, if you like, some sort of history. And what we find with these kinds of models is that we can very, very easily predict the score that a human rater would give. So in other words, we can model this and we can automatize this whole process of clinical ratings. Now, verbal memory deficits are a hallmark feature in many psychiatric conditions, notably schizophrenia. And so it stands to reason that if we can model aspects of the language features used in recall, that we can measure these verbal processes. So using similar methods to the previous slide, we have been able to automatically analyze the verbal recall and to mimic human scoring on classic neuropsychological tests. And again, the semantic features were those most predictive and able to differentiate patients, their unaffected siblings, and healthy control participants. So this proof of concept brings us to a few years ago, where we were able to then move assessment out of the controlled laboratory. So technological advances in the form of smart devices combined with speech technologies offer this promise of effective tracking and monitoring of the cognitive and clinical state of patients. So about 5 years ago, we developed and trialed a mobile app that remotely took patients through a series of repeatable verbal exercises, such as retelling a story they had been told, and variants of cognitive neuropsychological tests. And by leveraging natural language processing and machine learning, it was possible to assess those sound bites for signs of mental and cognitive state. And we tested this out on a few hundred patients living in either Norway or Louisiana in the US. So the study occurred within different languages as well as different cultural and legal settings. And we learnt many things. Firstly, if you take this kind of assessment out of the lab, we really need to have a lot of other experts involved, especially lawyers. If we take it out, testing out of the expert hands of an administrator or someone who is clinically assessing someone, we need to have very excellent and robust user engineering. And if we're going to frequently administer tests on a daily basis, for example, we need to have multiple versions with a lot of usability. To illustrate this process with my favorite test, the verbal memory test, what we did is we had participants listen to and retell stories. Then we had experts listen to the verbal responses and rate them for retelling accuracy. Our goal is to create an automated method of rating recalls that mimics humans, that performs as well as humans. So first we had humans transcribe the response recordings, and then we calculated the similarity of these transcriptions to the original stories using natural language processing techniques. The same procedure was used on transcripts derived using automatic speech recognition. Although the word error rate seemed high, the performance of the predictive models was still within the level of individual raters, which demonstrates the robustness of this kind of procedure. The linear model represented the human ratings well, with performance higher in healthy participants as compared to patients, which indicated an overall difference in verbal memory between the groups. But of course, the promise of this kind of work is to enable clinicians to monitor patients remotely, alert them to issues or changes that arise between appointments that could be life-saving. But there's a massive gap still between the success of successfully detecting a subtle difference or change and the real-world implementations of such systems to assist clinicians with a second opinion. A long-term goal is captured here on the left, an idealized desktop helper that could use both population and individual data to provide a precise estimation of the current clinical state of patients, a second opinion that could be used both within the clinic and for remote monitoring purposes. On the right is a hypothetical distribution of behavioral signs of agitation expressed via speech from a general population, that's the grey curve, and two psychiatric patients illustrated by the green and the blue curve. Now, a very uncommon value for an individual patient, indicated by the blue arrow, the hypothetical patient B, may well be within a common range of the population. Hence, it's really important to collect both population and individual means so as to avoid life-threatening misses and false positives that would negate the value and trust of such a system. Now, obviously, a skilled clinician familiar with these patients will adjust the threshold of intervention when judging, for example, the state of agitation for a known patient. But if we want machines to help them, then we need an enormous amount of data so that a machine learning system can also implement a more tailored thresholding that matches both the relevant population threshold and the individual personal threshold for that specific patient. However, an enormous amount of research is necessary to produce the magnitudes of data that can confirm or disconfirm this type of conjecture. And of course, probably as you've noticed, I'm only illustrating one of potentially many hundreds of dimensions of behavior here. So one of the great things about automatic speech recognition is it provides transcripts for analysis, precise timing data, and enables full automatization of the assessment pipeline. But the word error rates can be very high for speech generated in real-world settings with ill people, because these models tend to be trained on homogeneous groups in rather idealized lab settings. But nonetheless, we find that our natural language processing models can be quite robust despite high word error rates. And we've also found that in-house task-specific language models can reduce the errors of general language models. Since our goal is an effective AI-mediated clinical decision support system, there have to be computational safeguards in place to avoid spurious predictions and allow humans in the loop to review the data in settings where models could be unstable or bound not to generalize or simply don't make any sense clinically. And it's really important to detect which models are unstable by means of attribute and class-based outlier detection. So for example, attribute noise, that would be values of individual attributes that don't make any sense because they're erroneous or missing. Class noise could be a label that doesn't make any sense given the distribution of features for other data within the same label. So this is actually from a paper that was presented at a conference a few days ago. This beautiful figure here is a distribution of the first dimension of principal component analysis of features from my favorite task, story recall data separated by rating. The darker colored peaks on the left represents a low rating of 1 point, which increases by 1 point per peak to the lighter colored peaks on the right-hand side of 6 points. So an unsupervised learning algorithm for anomaly detection, in this case isolation forest algorithm, was used to detect outliers which are shown with a cross, and the color of the cross represents the human rating given to that example. So if we look at one of these examples, this is an example that was more in line with a feature distribution of ratings with scores of 5 or 6, but it actually had an expert rating of 2. So this is just an example of how even in a very simple test, it's extremely important to have computational safeguards in place. It's also extremely important to establish how generalizable models are, as well as whether they show inductive bias, because shortcomings can lead to insufficient accuracy on unseen data retrieved from different settings, such as a control laboratory or clinical setting versus remote settings, different populations, and different clinical states. And there's also the very real risk, at least in language databases, of this thing called the weird phenomena. This is the phenomena that many participants in these databases tend to come from countries that are Western, highly educated, industrialized, rich, and democratic. So it's the weird phenomena. And we already know that there are sex and gender differences that are creeping into these databases that we're using. Then there's an elephant in the room here. We work with language, and we just don't know how universal language agnostic the measures and features are. Yet about half of the world is not monolingual. In other words, about half of us speak at least 2 languages. And we just really don't know yet whether some of the differences we see are just subtle, insignificant, or actually clinical significant differences, depending upon whether we're actually assessing someone in their dominant or non-dominant language. We do know that we can get contamination in these data from our first language and also from dominant language, such as English. So there's a lot of really interesting work that needs to be done here. What we do know is that once clinical trials have been conducted, full automatization of the assessment pipeline is actually in principle possible. But we have a couple of problems here, and that we know that some of the tasks that we use to elicit speech differ in terms of their sensitivity, their specificity, and their temporal value. So it's arguably the case that precise and sensitive measures are not really useful unless we know what they're predicting is about to happen and when this will happen. In other words, the specificity and the temporal value. Will it happen today, tomorrow, next week, next decade, and what exactly is about to happen? At present, the goal of getting natural language processing models ready for personalized medicine has not been met. The current models are not individualized, and currently models are illness specific rather than person specific. Speech also varies as a function of sociocultural, linguistic, and contextual variables, but none of these factors have ever been systematically addressed in previous studies, and the field generally lacks computational methods for systematically addressing them. In the interest of time, I'm going to hold this. And then there are a lot of ethical issues that remain to be established. The excitement about psychiatric application of natural language processing models is tempered by this fear that risk about decisions about clinical issues are going to be made for spurious reasons, that the models might not generalize, that there are biases inherent in the data set that could propagate into predictions with harmful results. And we've recently argued, as indeed other people have, that the promise of clinical translation is much more likely to be met more quickly if the data models are trustworthy. In other words, if they're explainable, if they're transparent, and if they are generalizable. So my conservative conclusion is, at the moment, applying natural language processing models in psychiatry, the field definitely feels like the Wild West. We have proven that we can do very useful things with small data sets, but now we need to move from individual studies to the big picture of how this works on a larger scale. And to do this, we need much larger data sets and much more hardened methods to translate into the real world. So in most cases, the algorithms and models in psychiatric research that apply natural language processing methods, speech technologies, are really not ready to be translated into real clinical practice and programs of detecting risk of developing psychosis and monitoring treatment responsiveness. So I would argue that a lot of work remains to be done before this clinical translation is possible. Thank you very much.
Thank you, Britta, for your presentation. We have some questions that have appeared in Slido for you. So if you compare somatic diseases and psychiatry, are there shared challenges in developing artificial intelligence tools, or are the challenges very different as you see it?
Well, that's a great question. Yes, of course, the challenges are going to be very similar, and there are a lot of methods that we need to look in my field to areas that have made great progress. One of the probably very big challenges in psychiatry is the temporal aspect, that things change very quickly. So currently, we have been very poor at collecting data on a very frequent basis. It just hasn't been physically possible, and I think that could change. The other thing, that big challenge that we have is there is no specific test that tells whether somebody has diagnosis X or Y. It's a very imperfect science, that part of the diagnosis process. So I think the grey area of determining specificity is a challenge, and maybe that might not be important if the treatments are, if the focus could be treatment rather than necessarily focusing on what illness someone has, which unfortunately is where a lot of AI has been in psychiatry recently, has been focusing on this binary classification, which is arguably not very helpful clinically.
Thank you. And one short question before we move on. What is your experiences with Norwegian automatic speak recognition and their accuracy?
We have limited experience with this, and so far I would say that the experience is somewhat positive, more positive than I thought. I mean, of course, there's much more data, many more years, going on in terms of English, so English is bound to be more accurate. But what we find is that if we build models that are specific to tasks, you can get around some of the problems of not being a big language. So I don't think size matters if the focus is on building the language model that is specific to the task or is a bit more constrained. But I think if one was to use general language models to look within some of these very subtle nuances in psychiatric settings, I think that would be a very unwise situation. So I would recommend starting with very tailor-made models.
Thank you very much, Britta. So we will move on to the next speaker in this session, David Clifton. So he's a professor of clinical machine learning at the University of Oxford, and his research focuses on the development of machine learning for tracking the health of complex systems. His talk is named AI and Next Generation of Healthcare. David, please.
Hello, can you hear me?
Yes, we can hear you.
Fantastic. Many apologies. There were multiple rooms for the conference, and I was apparently I was in the wrong one.
But we cannot see you yet. Have you shared your screen? Oh, there we see you. Thank you.
Hopefully you can see me. Hello, everybody. I've just been given permission to share my screen, so I will do that immediately. And I have to say, I am deeply impressed to see a real live audience. I'm deeply impressed. There we go. Now, hopefully you can see some slides of mine.
Yes, we can.
Fantastic. Well, thank you very much for the invitation to speak today, and apologies for the tech hiccup to start with. It's I think a happy consequence of the fact that the organizer managed to put on a real conference. I see actual people in a lecture theatre, and I will remember this for a long time because it's the very first post-pandemic, let us say, if it's not too early, real conference that I've seen. I've done plenty of online ones, but never seen someone in person in a lecture theatre for a while. So yeah, that's greatly relieving, and well done for arranging it. I'm going to talk briefly today, of course, about AI techniques and perhaps a slightly different perspective, coming as I do from the UK. I don't do medical imaging. That's very well defined, obviously part of AI, but I do pretty much everything else, and lots of interests in common with some of the fantastic stuff that we've been hearing about this evening this morning in terms of electronic health records, natural language processing, time series data, and so on. Okay, so let me just give you a very brief overview. I'm here today. In fact, I'm actually in this office here. From the medical campus in the University of Oxford, and I'm actually part of an AI group. So it's fantastic. The one bit of secret sauce that I would say that I could share with everybody simply is just put yourself next to medics. Being 6 minutes away from 4 hospitals is a really big difference to being half an hour away. It really changes the nature of collaboration. So that's the simplest thing that I can recommend for quick and easy progress in healthcare AI. I've also got a lab, a little bit of a longer commute just outside Shanghai. This is part of the Oxford University labs, where there are 12 laboratories. Mine is the machine learning laboratory just outside Shanghai. It's a lovely place. Again, very similar priorities in terms of using healthcare data with AI to improve patient outcomes. One of the nice things about our lab in China is instead of a walk-in wardrobe, I have a very large walk-in computer, which I think is rather nice. It sounds like a jet engine. You wouldn't really want to go there to relax, but you can dry your hair in there. It's very warm. So it's just basically a walk-in wardrobe stuffed full of GPUs. I'm sure you know the drill. Perhaps a little bit differently to some of the speakers previously, we also have a Wellcome Trust flagship center, which is based in Ho Chi Minh City, of course, was Saigon in Vietnam. And I always say that it's really hard to do low and middle income countries research. It's the kind of thing that is very hard to get funding for, frankly. So the Wellcome Trust has been absolutely tremendous in giving us approximately a 9-year program in being able to really join the Oxford University AI lab, which I have, with our overseas research unit, the Oxford University Clinical Research Unit, which has been running for 30 years in Vietnam. And again, same problems: intensive care, predicting patient deterioration, improving health outcomes, but in a very different setting where resources are limited. And so AI and smart devices, of course, have a key role to play in being able to help people do more with less. We happen to be based in a very large infectious disease hospital there as well, which is of course very timely given the nature of the circumstances. Before I talk a little bit about the AI and what's under the bonnet, the hood of the car, so to speak, I thought I'd start at the end and give you a little bit of insight as to the things that have been coming out of the lab, because we're very hard-nosed. We focus on things that clinicians need, and that's the focus of our work, giving clinicians things, boxes, interventions that have got AI in them to help people. So I thought it'd be instructive, given the panel session that we've got coming up, just to show you some areas where we've made some impact, and we've made the jump from a lab into a hospital. It started off not in healthcare. It started off on jet engines, in fact, patient monitoring, just with very different patients. And if you've flown on the Airbus A380 or the Boeing 787, you've got my system sat on top of the jet engine, monitoring that patient, its temperatures and pressures, just like human beings. They're slightly more well-behaved than humans. You haven't been on the Eurofighter Typhoon, but that's also got the same technology on it. We translated those under the leadership of my then PhD supervisor, Professor Lionel Tarasenko, into the clinic. So this is the Oxford University Hospital's Emergency Department, where we installed these devices created by our university spin-out company of the time. These are Vicentia, which was for the longest time, for over a decade, it was the world's first and only FDA-approved patient monitor with machine learning in it. So it's really exciting. As a case study in machine learning and getting it into the clinic and getting FDA approval, it was pretty cool. What does it do? It basically takes vital signs from GE monitors or Philips monitors and performs some machine learning on them to be able to bring nurses back to the patient's bedside. You can imagine it being 10+ years old. The machine learning in there is a bit old-fashioned. It's stuff like random forest support vector machines. What we'll get onto later on in the talk is what modern machine learning can do for us, given the vast quantities of data that we've got. But for its time, it was an interesting and very worthwhile engagement. It helped a lot of people. It was used in hospital networks in the US, where they said it would be unethical not to use the system after they ran clinical trials showing that it worked. And that's the spin-out company that makes these things, called Vicentia. Again, under the leadership of my doctoral supervisor at the time, we created technologies that allow one to monitor vital signs using just a camera. So it's non-contact vital signs. Here's the patient. He's a neonate in intensive care, but the monitor is the camera, and we can get things like respiratory rate, changes in blood pressure, changes in oxygen saturation, heart rate, and so on, straight from the camera, which is again an interesting subject. This company is doing really well. It's rolling out these remote monitors to pretty large networks of hospitals right now, which is really good in infectious control circumstances. Particularly, you don't want to be touching the patient, so non-contact sensing is a good thing to do. I say I don't do image processing. There is a bit of image processing in there, as you can imagine, but it very rapidly becomes signal processing. Slightly differently, we have a company called BioBeats, which was recently sold to a large monitoring company was called Meadowpad and is now called Huma after they bought the BioBeats company. BioBeats, as you can see here, it uses wearables to perform stress estimation, primarily based on things like HRV and other parameters that you can get from pretty low-tech accelerometers and pulse oximetry. You don't necessarily have to have a super cool Apple Watch to be able to use these, but the market for these is white collar sort of insurance companies where you etc. where you want to monitor the stress of your white collar workers. Those are the areas where the case studies have been deployed so far. But it's a really interesting opportunity to do AI in a rather different setting. And then just to finalise, a recent success story, Sensine Health, the UK's first publicly listed company for clinical AI. And we floated this on the London Stock Exchange in August 2018. It's now listed on the UK London Stock Exchange, which is a bit of a different game. I'm used to academic practice, I'm used to libraries and books, and the London Stock Exchange is basically not any of that. But it was very exciting nonetheless, and this company is doing extremely well and is joining very large quantities of electronic health record data in the US and the UK with a really interesting business model to be able to support patient care and also be able to accelerate the development of medicines. Okay, so that's all the sort of the crunchy entrepreneurial type stuff, but obviously we want to think and talk about AI, and clinical AI. The way I see it, it's really hard actually to do this practice at scale. There's not very many places globally where you can do it. in a manner where you can actually get interventions into practice, because you need AI, and of course we've got in Europe and globally we're very lucky to have large AI networks like the LS network. In the UK we have the Alan Turing Institute, lots of good AI emphasis and AI people. As we've seen earlier today, several speakers have commented on how important it is to have clinical input and clinical knowledge, and I would really say, you know, we do not get out of bed unless we are able to meet our clinicians to construct models, ensure we're doing the right thing with our data, and so on. It's really hard, obviously, to do clinical AI, you know, from a bedroom, not talking to anybody with TensorFlow. You know, you're not going to get very far with that. And the third part of the puzzle is a big pile of data, because you need very large quantities of data to make use of modern AI, but that comes with it the obstacle that traditional old-fashioned AI methods like random forest support vector machines, etc., are not great at scaling to truly huge quantities of data. By which I mean we're probably up to about 2 to 4 million patients worth of crunchy electronic health record data, you know, which can go back to the 1980s. I mean, these are very large time series, and they're very rich in the multivariate nature of the data, and there's gazillions of patients. So just chucking those into a support vector machine really isn't going to fly. So there aren't too many places where you can do that globally, because you need to have all those ingredients. So getting that right is pretty important. Very quickly, what kind of data have we got? I won't over egg the pudding, because we've seen this previously. Vital signs, perhaps collected every hours or every minute, hourly if they're manual observations, as shown here on the right. We put these systems into Oxford University hospitals. These systems are now used by everybody, all patients in the hospital, actually. So we get all data from all patients all the time using the systems that we put into Oxford University hospitals, which is a good source of data, although sadly, you know, it's totally under the governance rules, we can't share it, but it is pretty enabling to have that. We've seen lab results, things like blood contents and so on. This has become pretty big in the world of COVID-19. We have real-time predictors of COVID-19 status based on the blood contents. And as I say, these can go back. You can see here this time series goes back to 1987. We've got a lot of data because labs have been collected electronically for so long. Increasingly, we're getting genomics now. So a lot of projects that we do are based on inference with genomics, perhaps proteomics and so on. Increasingly, you're getting genomics not just for rare cancers, but for all sorts of other diseases too, such as immune assays and Crohn's disease, ulcerative colitis. You know, there's a lot of genomics around these days. And then the kind of stuff that engineers love: prescriptions, diagnoses, noisy data, and so on. Somebody started typing. If I could please trouble the typist to put yourself on mute, that would be much appreciated. So we've got all these very noisy artifactual time series, none of which is more noisy than that which you get from wearables, of course. Wearables can be sampled at, I don't know, 100 hertz or whatever it might be, but artifactual data is the norm for a wearable, and fusing all these data together to produce things that are useful to the clinician are important. The kinds of schools of AI that go into this are maybe 5 years ago, everybody was in our field was doing Bayesian non-parametrics, so things like nested Gaussian processes, multi-output Gaussian processes, and so on. Really good for handling noisy data, but they don't scale to massive data sets because it's order n cubed in the number of data, but they're really decent predictors. So obviously these days, deep learning is a good solution to that. We prefer to use these two things in tandem. So performing infinite dimensional Bayesian non-parametric models over the univariate time series, but then fusing them using deep learning in an interesting way to learn motifs between data and so on. And as I touched on earlier, that can only get you so far. If you've got 100,000 patients, it's fine. If you've got 2 to 4 million patients, it really isn't fine. Your machine is not going to train optimally. So increasingly, we have networks to help train networks in terms of meta learning. Perhaps just as a frisson of methodological interest here, I'll quickly change gear and just talk a little bit about this last part. So if the data sets really are very, very big and rich and deep, is it the right thing to do to pour those into a support vector machine or chuck them into a convolutional neural network with and hope your graduate student comes up with a good network that produces a decent outcome? Unsurprisingly, very few of those networks have made it into the real world, and it's primarily due to their ability to overfit to the data set that you've got, of course. So being able to produce systems that generalize while being immensely complex is the name of the game, and that's the thing on the bottom right that helps us a great deal. Okay, so perhaps skipping forwards, here, let's have a look at a few, let's put a little bit of flesh on the bones. So imagine we've got time series that they can be, typically they're weeks in length for a hospital stay, or they might be years in length if it's a home patient, perhaps going to see their GP every couple of months or so. But we can fit to the univariate data a Gaussian process like this, and we fit it robustly so it doesn't fail. And then, but we're doing that with all manner of time series in parallel at once. So we've got maybe 50 to 100 of these time series, each being fitted independently. The Gaussian process now is sort of a pre-processing step, and these are being provided to deep learning systems that then can fuse, as I was saying, fuse those very large quantities of Gaussian processes rather than trying to crunch the original data. So this particular application is a little bit like the first one in the emergency department. It's trying to say in the whole hospital, you've got critical care outreach teams. Who should you send them to see? Should you don't want to send them to patients who are nearly dead, for whom an intervention can't matter, the red patients. You don't want to send them to patients who are fine, the green patients. You want to send them to patients for whom an intervention would matter, the amber patients. So we found this to be really, really very, very exciting. This was a large Wellcome Trust funded project called Haven. Perhaps I'll skip the student teacher part here. So this is what I was talking about previously. This is based on some work published, I think it was in the middle of the pandemic in ICML. And here we've got student networks, by which I mean this is just a cartoon. We're potentially talking about very deep networks with latent representations of the input, like autoencoders, perhaps some temporality, such as LSTMs. So we've got lots and lots of individual models that you train to your data. And you might say, okay, I'm going to predict sepsis with this model. I'm going to predict tetanus with this model. I'm getting, all sorts of other cognate infectious diseases, perhaps based on the same data. I've got lots of different students learning from those data. And then I've got a data set of 4 million patients. Is it optimal for me just to tip 4 million patients into TensorFlow and hope something good comes out the other end? Answer is no. So what we typically do is we construct a teacher network as well. And the teacher network is constructing a curriculum. It is teaching the students how to learn. And this is a reinforcement learning algorithm. So the teacher is learning to take spoonfuls of data from the big reservoir that it's got and to spoon feed the students in an optimal manner. The reward is increase in predictive power, AUC or equivalent. And as I say, it works in a reinforcement learning way. So the teacher actually learns which data students need to see in order to learn better. And unsurprisingly, the teacher learns that you need to show students easy data to start with, easy data, and then you show them more complex, ambiguous data later on, defined in a certain way. So it's a really interesting process of being able to intelligently determine where in your training set you should go to get your mini batch to train your committee of deep networks, which are students. So you've got a teacher training students, and it does pretty well. And then finally, just a few cartoons to show you in the last 5 minutes what meta learning can mean for us when we've got gazillions of data. How can we improve these situations? Data augmentation, for example, in imaging is really well known. You'll take your image, you'll mess it up a bit, you'll rotate it, you'll transform it to augment your data set. But we can also do the same with time series data as well. So we can generate loads of artificial data, brackets, electronic health record, nasty artifactual time series data, rather than imaging data as we might otherwise be familiar. So we can augment the potentially small number of data that we've got, because as I said, we've got 4 million patients, but how many patients have we got with Crohn's disease? maybe 2000. So you might want to augment them and their time series data accordingly. And you can, obviously the generative adversarial network is really good for that. Conditional GANs we like, of various flavors, as shown here. I won't get into the details because of the time, but they're conditional on the on pathology. So you can say, generate me please some serious sepsis data, generate me please some moderate sepsis data, generate please some etc. And so they're conditional based on the pathology that you'd like to generate. And in this particular application, we were looking at what hand, foot, and mouth disease, which is an infection, tetanus, cardiovascular disease, and some canonical physionet tasks, and showing that these are boosts in AUC if you use various conditional GANs. So you can boost your AUC by 10, 15, 20% using these kind of methods. We like that. So that's a particular paper called PlethAugment. Okay, so just quickly whizzing through a few cartoons just to show you a few fun things before we finish. Contrastive learning, becoming a bit popular as a buzzword. It's saying that I've got two classes of data, circles and triangles, and I've got a new fella that comes along. I would like this thing to be attracted more to data to which it has something in common and repulsed from things from which it doesn't. So you can see the new data point is encouraged in the network parameter space to look more like things it looks like. And here's an example using ECG. What we're doing is we're at the same time as making predictive tasks like what's wrong with this person's heart, we're also saying at the same time what groups of patients exist in the data. Perhaps I won't go into the details because of time, but really the outputs of that process is a set of prototypes. So it's not just left ventricular hypertrophy, which is a nasty heart disease. It's left ventricular hypertrophy type 1, type 2, type 3, for example. And that really boosts performance in the machine learning methods because it allows us, this particular paper goes into details, it allows us to have models which are specific to the phenotypical groups that the patient data falls into, which is again another way of trying to navigate your way around these nasty big complex data sets. Continual learning, I think I'll quickly touch on, where continual learning is teaching a network to do lots of different things. So it's very old-fashioned to say, I've got a data set, I'm going to construct a model, and then I'm going to predict one thing. And now I've got a different, maybe the same or different data set, I've got to predict something else, I'll construct a different model. Why don't you, because they're operating on cognate inputs, take the same model and ask it to do multiple things? You can predict lots of different types of cardiovascular disease and or infectious disease or whatever it might be. But networks are prone to catastrophic forgetting. They tend to forget things from the past and they only remember the most recent future. So you've got data from multiple different distributions, and then what we would seek to do is find those data that are most informative and somehow store those in a buffer. So this notion of continual learning, the notion of continual learning helps us to do that. It says, if I've got a network, isn't it better for me to help that network to predict a target infectious disease by allowing it to predict other infectious diseases as well? And continual learning is that notion of doing lots of tasks one after the other and storing informative data to allow you to do that. I think in the interest of time, I've got a whole bunch of applications I could talk through, but I think what I'll do, I will get to the end and I will say thank you very much to our sponsors. Just to point out, we do sort of scientific work, top left, let's say, funded by the UK Science Councils and the European Science Councils, do interesting pharmaceutical collaborations for medicine development and things like that. So it's a different group of projects. And then at the bottom, as I was saying, low and middle income work. We're very grateful to these funders for really helping us to do that. It's a pretty big group. There's a lot of good stuff going on in clinical AI at the moment. I'd be very welcome to go into any more details during the Q&A. So thank you very much for your attention. It's a great pleasure to talk to some real people, even though I'm doing it remotely. Thank you.
Thank you very much, David. So as we are rounding off this session, so to all speakers presenting online today, you will get the gift in your mailbox, consisting of some reindeer meat and some cloudberry jam. Before we move on, we have a couple of questions for you from Slido. And first one is, how do you create a good environment for creating spin-off companies to transfer technology into the clinic?
Oh, that's a great question. Can you still hear me and see me? Hopefully I've stopped sharing my slides. Can you see a human being waving at you? Yes, I can see it in the back. I can see myself in the background. Great. Good question. I can't take much credit for creating the environment. That's really obviously an institutional activity. And I've got to say, the sheer volume of spin-outs that come out of my host institution is such that they sort of knocked the corners out of that process pretty well. It's helped by, you've got to have venture capitalist backing. So I think our university has one of, if not the largest internal venture capitalism fund for funding scientific businesses. I think that's a key part, which came from some alums who'd made their money in hedge funds. I think having the trust in academics to know what is scientifically interesting is important. So plenty of institutions I collaborate with, their tech transfer offices say no a lot based on quite limited information. And I have to say the answer in our tech transfer office is usually yes, let's try it and see. Maybe they're less risk averse, I don't know. And then, yeah, it's down to critical mass. I guess once you've, I'm riding on the coattails of successful people, standing on the shoulders of giants, whatever your cliche might be. You know, the previous generations have made it work. They've done cool things, and once you've got that ecosystem of investment and people who are looking beyond the university's horizons to get involved, then I think, you know, those success stories just take a bit of time. And at the start, you have to be a bit risk averse. It's a tough one, particularly in the modern climate. I can see that it's not easy.
Yes, thank you very much. I think also that is a good, perhaps, introduction to our next session, which is a panel session. So we will have a panel session regarding the gap between development and implementation. So this session will be led by Tor Ingebrigtsen. He's a professor of clinical neurosurgery at University of Tromsø. And for this panel session, you can ask questions in Slido, and I will be directing them to the panel at the end of this session. So Tor is participating here on stage, and our panelists are participating digitally. So stage is yours.
Thank you. So good morning, everybody. So we have 4 panelists today. David and Britta and Bart have been introduced already. I hope you're all still with us. And then the 4th panelist is Ishita Barua, and she's a MD and a PhD in the Clinical Effectiveness Research Group at the Oslo University Hospital and the University of Oslo. And currently, she's a Fulbright Fellow at Harvard in Boston. So I think, Ishita, it's still in the middle of the night or very early morning. So are you with us?
Yes, can you hear me?
Yeah, we can hear you, and we can even see you. Good morning. What time is it?
It's 5:41.
Wow, that's great. Okay. So the plan is that we have invited you to comment on the presentations from the 3 previous panelists who have presented already. So I'll just start out by handing the word to you. We look forward to your reflections about this question about how to bridge the gap. So please.
Thank you. So thank you for having me. I'm very grateful to be part of this distinguished panel. What we all four have in common is obviously that we are doing research in the application of AI. My research focuses on applying AI in colonoscopy and colorectal cancer screening. And as you correctly said, I'm currently in Boston as a Fulbright scholar, and I'm conducting a clinical AI trial at Beth Israel Deaconess Medical Center and Harvard Medical School. So I could really relate to the work that Dr. Gertz does and the need for more validation in clinical medicine. Dr. Gertz mentioned and highlighted that we need to be more aware of bias embedded in medical research in general, and the need for developing and vetting algorithms as a team effort. I second that. There is no question that the appearance of big data and machine learning in medicine offer an exciting chance for revolution, but revolutions demand also greater scrutiny, not less. So this scrutiny should involve a reality check on the promises of machine learning powered precision medicine and an enhanced focus on the core principles of good data science, trained experts in study design, data system design, causal inference, asking clear and important questions using high quality and representative data. I also find it very interesting that Professor Alveog concludes that in most cases, the algorithms and models in psychiatric research that they are not ready to be translated into real clinical practice and programs for detecting risk of developing psychosis and monitoring responsiveness. This pretty much sums up the situation for any leading clinical fields in medicine as well, not just psychiatry. We have that in gastroenterology as well, and I'm sure radiology also have their challenges. And although news media is filled with enthusiastic stories about novel machine learning applications, a systematic review from BMJ from 2020, published by Nagendran et al., makes for very sobering reading. In this study, they were comparing the performance of deep learning versus health professional assessment in diagnosis of various diseases from medical images. And only 20 out of the 82 studies identified evaluated the performance of their algorithm in an external cohort. And only 14 out of those studies compared this out of sample performance with what of health professionals. And this number is alarmingly small, especially given that many of the studies were actually very flawed. And the authors found that the reporting standards were typically poor, internal validation was weak, and perhaps most worryingly, the model performance was often evaluated under completely unrealistic conditions, and they had very little relevance to routine clinical practice. And I stress that routine clinical practice, which is how you will implement studies or implement AI. If you cannot show any true clinical validation, then doctors are not so willing to take that practice in. And for example, there is little use comparing the performance of a machine learning algorithm with health professional judgment for making diagnosis from medical images without providing further contextual information about the patient, as this would never happen in practice. And today we have mostly traditional in silico evaluation.
What happened? Okay. So David and Bart and Britta, are you still with us?
Yep, absolutely. I think something happened under the Atlantic.
I'm afraid we lost Ishita, but I'll just challenge you and comment a little bit on what she said so far. So let's start with you, Bart, as the first presenter this morning.
Well, there's not a lot to disagree with in a way, what has been said so far, I guess. I think trust is the key word, at least for me as a clinician, or and looking at what my colleagues are taking in. And that can actually be very hopeful in terms of I've been doing a lot of innovation, bringing new devices to the practice, where a lot of my oftentimes correlated with age colleagues found it kind of hard to implement something new, despite all kinds of papers going with it. Here, and of course it has to do with the case that I presented was short cyclical, as in there's an alarm problem pops up kind of immediately. That in that setting specifically, it was actually easier to build trust within one case even. So that I think that's hopeful, but I think we need to really pin down what this clinical evidence and clinical safety is for these kinds of tools. And guidelines are in the making, a number of them. Like I said, happy to be part of them. Also thanks to one of the fellow speakers here. I think we need that kind of pinning it down and telling mostly tech companies that don't have the background in healthcare what is needed to get to actually trust these tools and really pin down the biases before we can actually expose our patients. So I only concur, a bit boring, but I concur with most what have been said so far.
Could I just ask you the application that you showed us about detecting low blood pressure in the ICU? Is it in routine use, or did you stop using it after the trial you presented?
No, I think since then we've basically treated or used it in the treatment of about 15% of all our cases. So in the OR, that means about 1,500 patients a year, up to 2,000 patients a year. The downside of being an academic and working in such a close relationship with the company is you don't have a saying on the sales and marketing side. So the price is now coming down to a point where actually more people can use it. So we now see people in France taking it in while it's becoming more affordable. So that for me was a great learning, and actually one of the reasons to start my own company. But yeah, I think what we've seen is basically thousands and thousands of patients now being treated with that tool to go with. Yeah.
So, to the technicians, did you manage to get Ishita on again? Yeah, she's there. So we lost you for a few moments in the middle of your comments. So Bart just reflected a little bit over what you said, but maybe you would like to complete your reflections, please. Well, we can see you, but we cannot hear you.
Now, thank you so much. I'm so sorry about the technical problems. Yes, I think I was talking about in silico evaluation of AI. So in silico meaning research performed on computer or via computer simulation. So increased scrutiny of AI applications in healthcare highlights the need for real-world evaluations for effectiveness and unintended consequences, and the complexity of healthcare compounded by the user and context-dependent nature of AI applications. It calls for a multifaceted approach beyond in silico validation and evaluation. And I believe the lack of validation of clinical AI tools from prospective studies is a challenge that doctors and healthcare professionals with domain knowledge need to address and speak up about, especially to our colleagues outside the medical community. Our understanding of when AI tools are ready for clinical applications and implementation is not intuitive to others, especially what levels of risk and harm we will accept for AI algorithms, what kind of black box that we will accept. Actually, that's none. In medicine, there are no room for black box. And so there are so many aspects about clinical medicine that are unique and differs from other industries and fields, and that understanding can be difficult to establish if you haven't worked as a doctor maybe or a clinician or have that domain specialization in your team. And I think lastly, I would also like to applaud Professor Clifton's focus on the discrepancy between the global population and the global health expenditure. AI could prove to level the field and offer solutions globally. There's a huge market for that. But I think in order for us to get there, I think we need to have more clinical validation. And that's kind of like the bottleneck for clinical implementation, I think, at least from a research perspective.
Okay, so let's move on to you, Britta. You kind of gave an impression towards the end of your talk that you, I got the understanding that you think that implementation into clinical practice isn't very close yet. So please.
Right, so I'm very, very conservative, maybe because when I started looking at this 20 years ago, I thought that we would be at implementation a long time ago. And I noticed in Bart's talk that he talked about I think it was right, the average 17 years of bench to bedside. So we've gone far beyond that. And I'm getting older, my hair is getting grayer, and it still feels very, very far away. And I suppose there's maybe 4 points that I could mention. So when I originally saw these speech technologies being used to rate student essays over 20 years ago, I thought, wow, this is really great. This will get rid of some of the variability, some of my poor ratings that don't match anybody else's. And the problem that they were having with that technology at the time was there was a lot of problems of trust, that teachers were going to be replaced by machines, and that had a surprisingly destructive effect on that field for a while. But now, of course, these software exists and it's part of everyday life. And so I became very optimistic that this could be the same for the clinical field, that, with, everybody having these technologies, Siri on their smartphone, that it would become more normalized and there would be a bit easier to develop this trust. Trust is a big issue, and that was really my first point. I think there's a lack of trust by clinicians, that there isn't this beautiful collegial interaction that David talked about existing that is so important. I think there's a massive gulf between people working on models, and it feels like we are working on models that aren't necessarily going to be what are going to be perceived as useful in the clinic. The vast majority of work in my field is about developing categorization models. So whether somebody is sick or not sick, whether if that's clinically validated, I can't see that necessarily being useful when we have such complex nuances of illness and severity and points that we have to intervene for treatment. And that comes to my second point. The reason that I've been very conservative is when I embraced the idea of continual monitoring. I thought, well, if we can collect loads of data, then we'll be home and dry, because instead of having this snapshot of testing somebody every month, every 6 months, and missing when there's a relapse process, if we just have more frequent data, we'll be fine. There are so many different dimensions of data to be collected, and at this point we just simply don't know how to interpret it. So yes, we can have hundreds of data channels, but at this point we really don't know how to calibrate that and understand what is my individual variability versus what is a threshold for some clinically significant behavior that has some clinical value. And then the third issue, which I've started to notice is a really uncomfortable elephant in the room, is that since I work on diagnosis through language, through speech, there are so many nuances in language and speech that we just don't really have the database yet to know what is clinically relevant to that particular individual, to that particular diagnosis, and throw it all together, all these hundreds of different variables that we can get from language. What is specific to Norwegian, or specific to Mandarin, or specific to English? At the moment, there has been a problem that most of this research has been done in the English language, and I get a very strong feeling that the gap between English speaking people and the rest is becoming very, very big in this area, and that worries me from an equity perspective. I think, yes, and then we've faced a lot of complex issues pertaining to law, legal issues pertaining to speech, even if we don't solicit certain things in our various assessments. If somebody reveals something that could be, potentially dangerous to somebody else, or or themselves, we have to have the capability to detect that in real time, and that is actually more problematic. So just to be able to collect data, we also have the moral responsibility to be able to analyze it immediately, and that is a challenge in of itself. So I guess those are my 4 points.
Okay, so then we move on to you, David.
Thank you, Tor, and thanks for the comments, Ashish. I thought it was really insightful. I guess, I think panels are more fun when people disagree with each other, so I'm going to force myself to disagree with you, because everything you said was very sensible, and I totally agree with Bart. If we, I could very easily go with everything you said. I think I'd like to take you up on the black box part. Let's say one thing that I've noticed is that AI is, maybe it's just my particular sub niche of clinical AI, but we produce a lot of scores, predictive tools that summarize a complex condition using a number. And clinicians are quite happy to do that themselves. They've got scores, as you know, for every single condition under the sun. You get one when you're born with an APGAR score, you get one at end of life with an Apache and SAP score in the ICU, etc. And they summarize heterogeneous conditions with a number, and if the number goes up, you care more clinically. And nurses start to take more interest, etc. So AI is just another means of doing that, and we produce scores. And the method for producing the score, ideally, is explanatory. I totally buy that. Computer says no, probably doesn't fly as a paradigm. But how many times have you seen a clinician use a SAPS or Apache score and then go back and say, wait a minute, let's look at the beta coefficients in our logistic regression model and see why we're getting that Apache score that we are? Never happens. So when you're evaluating a clinical tool, like that, say, for example, that historical example I gave you, it's got pretty simple machine learning in there. It's kernel density estimation based on probabilistic methods of 10, 12 years ago. But and it got FDA approval, but as I say, but it doesn't say why it's producing, it's got no causal inference in it. That's a really exciting part of modern machine learning. It simply says this patient's sick, number goes up, get a patient to the bedside. And, it passed clinical trials, passed FDA approval. It seems to be selling well. And like I said, it's unethical not to use it, according to University of Pittsburgh Medical Center. So the reason for that is, as I say, scores matter. Nurses talk about the score as if it's a new vital sign. They say, oh, what's the status index? And they don't say, why is the status index that? Or they might do once they get to the bedside and want to start unpicking it, So I do take umbrage with, people saying, oh, black boxes, AI is never going to work. Because actually that doesn't represent clinical practice. And in fact, a lot of boring logistical regressors are black boxes as far as the medic's concerned. That's a long way of saying it. I suppose another problem, just I think touched on what Britta was saying, is the incentivization. What the gap between guys working on models and medics getting their filthy hands on patient interventions, is a pretty big gap, obviously, and that's what Britta has talked about, and is the name of this session. I guess it's motivation. So as a professor of AI, I'm not motivated at all, career-wise, to put things into hospitals. I'm judged on how many AI papers I got out over the last 7 years, according to the UK government. I mean, every nation's got its own weird assessment metrics, I'm sure. And I get funding based on my Google Scholar, whatnot, or my and or track record of spin outs, whatever it might be. The incentivization is really not there at all. You have to want to do it. It's almost career limiting for young engineers in academic science to try and put something into the clinic, because it takes them away from publishing and all the things that they need to do in future. So yeah, I haven't seen a good solution to that yet. Sadly, I mean, the only way I made it work was to do both at once, and it's not a great work-life balance. Yes, you've got to satisfy 2 masters: the publication master, and also your career interest. So, if anyone's got any thoughts on how to square that circle, please go for it.
Okay, so leading this discussion is a little bit difficult because I only see you behind my back and I only see one of you at a time, and the sound is quite bad because the speakers are in the reverse position here for me. So I don't know, do you have any questions from the audience?
Yes, I do. So maybe I will ask David first, since he was the last speaker talking about the black box problem. So I think we can agree that the linear regression is as much a black box to nurse or a clinician as machine learning can be. But do we have to just accept the black box problem, or is there anything we can do about it, or perhaps approach the problem in a different way?
Hey, absolutely. Good question. I would say, just speaking up, so the audience in the lecture theatre can hear us. Yeah, obviously explanatory AI and saying why you did something or why you made the call you did is critically important, and that's a good starting point to engage on a new project or a new intervention with a clinician. I just playing devil's advocate, really. In practice, when you are running things through a phase 3 clinical study and you're doing an RCT, no one's really unpicking the details, but it's important to have the details so that you can close the feedback loop. It's important to tell clinicians something they don't know about their patient or something they don't know about their data set or whatever it might be. You can't. I don't think it's not very more generally interesting when you're doing a complex intervention, like getting a critical care outreach team to a bedside. If that critical care outreach team has got some is told why the machine is doing what it is, obviously that's a benefit. Just saves everybody time. I'm just saying sometimes it's not on the critical path for a phase 3 RCT to have the explanatory component. Often it's predicated on a statistically significant improvement on primary outcome. In fact, it always is.
Okay, so maybe not what you're prepared for, but I'd like just to wrap this up with asking the four of you, what are the most or the lowest hanging fruits if we should try to be guided by an application, an AI application that would save most lives or most quality adjusted life years? What would be the lowest hanging fruit to approach if we want to use this in the clinic as quickly as possible? Would you proceed in the ICU, Bart?
Oh, I don't think you'll make the most impact on lives, but that may be a bit detrimental at my own specialty's expense. I think the more impact you can have is actually tailoring your preventative measures. There are multiple tools, and I think data privacy is a big issue in that domain, but where do we target our preventative measures? Where do GPs help getting people off smoking? It's that kind of stuff. And I think there are plenty of tools out there already that actually can tell us which households are at risk of poorer health. And there are multiple interventions that we can do there. It's a bit boring for most. It's not hard clinical action, but I think if you're looking at impact and creating better life quality, longer life years of good quality, then that would be the area to tailor, I think.
What do you say, Britta, within psychiatry?
I actually really don't know. As I understand it from this conference last week, where it was a lot about these methods, the field would suggest that it's just around the corner to predict suicide with some of these monitoring techniques. I'm not sure I would agree, because I think that one also has to get the buy-in of people wanting to be monitored who are maybe at risk. And that's always the issue here. There's lots of ways that these things could be used to monitor drug drug use, treatment success in psychiatry, where there's often comorbidity, but it's whether the people are actually willing to be monitored as frequently as would be necessary. So it's there have to be many conditions satisfied, and the cultures will differ, and there will be different niches, but I don't think there'll be one thing that I would invest all my money in.
David.
I guess I've talked a lot about hospital data, mainly because it's really rich. You get tons of it. But I think one of the most impactful things that I've seen from the pandemic is working in primary care. And primary care data is not really so easy to get. You obviously talk to a hospital network, you can get a couple of million patients. Talk to primary care, what do you get? By primary care, I mean your family doctor, your general practitioner, whatever it might be called. We're very, very lucky, I think, in the UK to have a centralized facility, so we can get access to about 55% of the UK's primary care records from one data set. And I think that's really interesting and impactful. The data challenges are different, like I was saying. You don't see your GP 5 times a second. And when you go to your GP, he's not measuring 244 data points. It's a very different game, but there's a huge amount of stuff that people could do there. I think that's an exciting area of growth.
So okay, so then you get the final comment, Ishita.
Yes, very interesting and very difficult question to answer, but I think I agree with especially David highlighting GPs and primary care physicians and data from there, but also from wearables. I think if we could have a way of actually using that data, for instance, through a blood pressure, for instance, depends on the outcome that we are looking at. That would be my guess, actually.
Okay, so thank you, everybody. I must say that I think it's a very interesting discussion. To me, it sometimes becomes clear what the outcomes that we try to predict and influence actually are. I think it's very important in this research that we are as specific as possible about not just surrogate endpoint, but very well defined clinical endpoints. And I guess we'll come back to that a little bit after the lunch. So then thank you, everybody, and enjoy your lunch.
Thank you very much. So, of course, you cannot leave before you get the proper instructions. So, for people present here in Tromsø, there's a COVID lunch waiting for you upstairs. You have the same designated seat number upstairs as you have here. And number 1 to 44, you will be seated in the back of the restaurant, 45 to 73 in the middle, 74 to 98 by the stairs, and the rest of you at the balcony. I think it's an indoor balcony. So just go upstairs and signs will guide you to your seats. Lunch will be for 1 hour, so we will start again here at 1:10. See you then.